This is an orthokeratology case where the patient has a fair amount of corneal toricity, about 2.25 diopters in the right eye and 2 diopters in the left. And the question was how to go about designing a lens for a patient like this, for how to decide on what type of lens to design. And so I'll just kind of go over my thought process. When I look at the baseline topographies, I usually like to look at where the toricity is. In this case, it's not fully contained within the pupil. We can see that the toricity extends out a little bit farther. It doesn't look like it's all the way out to the limbus, but it does go out farther than just a few central millimeters. In the left eye, there's a little bit less of it, but it does still extend outside the pupil a little bit. So the farther out it goes, the more difficult it will be to get rid of. And so that's one maybe weight I put on the scale, leaning towards doing something specific to address the toricity. The next thing I look at is I compare how much cylinder is in the refraction compared to how much toricity is actually on the cornea. So here we have a basic lens, have not gotten into a reverse geometry ortho-K lens. This is just kind of the default that Wave gives us when we put in the patient's prescription. So there's a little bit more corneal toricity than there is in the refraction, and a handy shortcut is to just click on the over refraction box here, and Wave will predict that if we sphericalize this cornea, if we get rid of all the corneal toricity, the patient will have about 3/4 of a diopter of, against the rule, astigmatism, and that's most likely lenticular. So in this case, we actually don't want to correct all the toricity that's on the cornea. A good average is we can correct maybe about half with a conventional lens. So if there's 2.25 diopters of cylinder, we would expect to correct about a diopter of it just with a regular lens, and that would leave us with a diopter and a quarter approximately, or 1 1/12, and that cancels out pretty well with the internal astigmatism that's being measured. So in this case, we don't really need to correct all the corneal toricity. We expect we'll get about half of it anyway with a conventional design. So I don't think we need to do anything real specific with this lens, although I would steepen the vertical meridian just to make sure we don't induce any with the rule astigmatism. We definitely want to correct some, but we don't need to correct all, and we especially don't want to create more. So here's an initial lens designed in GSIM mode. I went with a pretty big diameter, 11.7 is the largest we can go before Wave considers it a semi-scleral lens. And this patient had a pretty large cornea, a little bit over 12 millimeters across. So I'm going with the largest lens that we can go with. Everything is pretty standard. And if we go into the freeform view of this lens, we can see now the lens is a little bit steep at the back edge of the reverse curve on the temporal side, and on the left side we're getting good bearing. So in this case, and this is just because the temporal side of the cornea is a lot flatter than it is nasally, so I would actually go ahead and redesign this lens in freeform to get better bearing around the edge of the treatment zone. Here we now have a freeform lens, and we can see that it's, according to the graph, better aligned all the way around. When we look at the back surface, we can see that the curves nasally are a little bit steeper than they are temporally, and that matches up with the representation of the topography that we see here. So with this lens, the last thing I would do is what I mentioned earlier, steepen the vertical meridian. Wave lenses can sometimes have a tendency to sit a little bit loose in the vertical meridian, and if that lens is loose, it not only makes it more difficult to mold out some of the cylinder, but that lens can also even induce some with the role of astigmatism. And we definitely want to avoid that. We're trying to correct anywhere from a diopter to a diopter and a quarter of it. So in the vertical meridian in 50% mode, in order to tighten the lens or get it to bear down on the cornea more, we're just going to click down on the boot dot. And drive this lens down into the cornea. We can do the same thing inferiorly. Wrong way. I'm going to go one more and get rid of that unusual curve. So now we have a lens where the sagittal depth and the vertical meridian is a little bit greater. It should meet the cornea a little bit sooner. And it'll look like we have a lot of central clearance, but everything's relative. We're just making this edge or the periphery of the lens closer to the eye. So this is a design I think I would go with for the right eye. Let's take a look at the left eye. Here's the default lens for the left eye. We can see there's a little bit less corneal toricity here, same amount of cylinder in the refraction, and if we look at the box, Wave predicts that if we sphericalize the cornea entirely, we'll have a quarter diopter slightly against the rule, slightly oblique. And so what this tells us is, for the left eye, we actually want to mold out just about all of the corneal cylinder, close to 2 diopters of it. Otherwise, we will be left with residual cylinder in the refraction with the rule. So in this case, because we're really trying to mold a fair amount of cylinder and it's not completely central, I would go ahead and design this lens with an oval optic zone and toric demand curves. So here's a lens for the left eye, again in G-Sim mode. And if we look at the topography down here, there's not as much asymmetry. And we can see that this lens does seem to fit a little bit better than the initial lens did for the right eye. So in this one, I think we can stay with G-Sim. We don't necessarily have to go to freeform. It's also a little bit easier to design a lens for astigmatism when it's G-Sim as opposed to freeform. There are fewer adjustments that we need to make and keep track of. So the way to do an oval zone is to for with the rule of astigmatism, we're going to go into the vertical meridian and decrease the OZ and IC by about 0.6 millimeters respectively. So this will go to 5.6. And this will go to 6.2. For the blue dot, I'm going to take care to not make the new position higher or lower than the original. I'm going to leave the lift change at 0. You can see that in the upper left yellow window. And we're going to shrink this to 6.2. The vertical placement of the red control point is not as critical at first because we're going to change it anyway. So we were originally, well, the power changed a little bit. Oh, that's because we were in 100% mode here. So what we need to do is move this back. We'll undo these changes. Okay, we want about a 1.4 to 1.5 demand here. All right. So we want to change this to 50% and then move these again. Okay, and you can see the oval shape of the optic zone now. Our demand here was about 1.4, and whenever we are looking to correct cylinder, I like to put the full amount at least into the differential. And the differential will be the differential in the power. So 1.4, if we're trying to crack the diopter in half, our new demand, at least for the vertical meridian, will be about a plus 3. So still in 50% mode in the vertical meridian, we're going to go up to a plus 3 power. Because we're in GSIM mode, freeform view, but a GSIM lens, whatever we did superiorly will be automatically reflected inferiorly. So we have a 3 diopter demand there, about a diopter and 4/10 or 5/10 here. So we have our differential of 1.5, and this will mold more cylinder than the lens we had for the right eye. But that's because we want to mold more here in the left eye. So those are my thoughts on deciding whether or not to make a lens specifically for cylinder and what to do when I want to correct cylinder. Hopefully this is helpful and gets your patient on his or her way to seeing well with as few lens changes as possible. So best of luck. Thanks for watching.